I was contacted by a friend of the university who presented this opportunity to partner with the Historical Society of Harbor Springs. And so we saw this great opportunity to engage our students and to augment their education and have them become involved in the exploration and the preservation of the AHA, which was a boat that was built by Ephraim Shea.
Ephraim Shea, he made his name in locomotives, getting timber out of steep areas, so smaller locomotives using his engines.
With that success, he was able to indulge in his other interests, naval architecture being one of many.
My reaction to seeing the AHA for the first time was how unique its shape is to modern vessels. The shape is very whale-like, which makes sense, the inspiration at its time, and it's also one of the first metal pleasure crafts, so it definitely wasn't made to be like every other boat of its time period.
The bow is very much a wave-piercing bow that you see in a lot of contemporary vessels these days. But when you start looking at the stern, you start to see some odd shapes there, more organic, a lot of flowing features.
It's about 50 feet long. It has a full midship section in order to fit the locomotive, and it's had several different deck designs through its life. I don't know precisely why Ephraim built the AHA. He lived in a very beautiful part of the world that's surrounded by water. And I expect that he just had a personal interest to be able to design a vessel that he would be able to operate near his residence.
So the goal of the AHA project for us was to kind of explore how hydrodynamically efficient Ephraim Shea's AHA was and kind of validate, what speeds it could have gone in Little Traverse Bay when it was in use.
The process to measure, model, and test the AHA started with us going out to Harbor Springs, as they have it on display there.
We did length measurements and we did beam measurements and all the physical measurements that we could.
Collecting hydrostatic data, so the weights data and where the center of gravity, center of buoyancy is, as well as collecting wave data, kind of establish what kind of sea state it would have experienced in Little Traverse Bay.
We looked at historical weather buoy data for several years, took all those data points, and then processed it through MATLAB to create those different conditions.
Of course, being from the 1890s, there were no structural or engineering drawings, so everything had to be recreated. Thankfully, the Historical Society at Harbor Springs had thought ahead and they actually paid for a 3D scan of the vessel, so that saved us a lot. And then, of course, that 3D scan is of a hull that is from the 1890s. It's been run aground, it's been left abandoned, it had bullet holes in it. The nose was canted off by probably 5 to 10 degrees because of how it had been left for a while. So it's not something that we could just go and immediately take that scan, even if it gave us perfect geometry that was usable, and have it produced. The students had to use their engineering mind, their naval architecture senses to basically say, if this vessel were in pristine shape, what would it have looked like compared to what does it look like now?
At first I focused on creating the 3D model of the hull and kind of preparing it for manufacturing, making actually solid surfaces. And this was kind of an interesting process just because the hull being so old, there was no 3D models or any lines drawings of it.
And Kobe took that full-scale model in Rhino and scaled it down to 8 feet, which is about the size that we wanted to test in the tank. And then we sent it off to be manufactured outside the US, and we got it here. We did modifications to the model, and then we tested it in both calm water and seakeeping.
The towing tank is a 110 meter long by 6 meter wide by 3.5 meter deep body of water. Built originally in 1904, it is 750,000 gallons of fresh water. Basin like this is used for anything from education all the way through commercial work. We do governmental research as well, and we can test anything that is pulled through the water, moves through the water, and anything that is under the waters.
two types of tests on the AHA. We did calm water resistance. So how did the AHA fare when being pulled along calm water? What were the hydrodynamics of it? And then we also did seakeeping tests. So that was the AHA and actual waves. We ran the wave maker and created a specific set of waves, a specific height and a specific distance apart in accordance with the weather data that I was researching about. And we ran the AHA through that as well.
The most exciting part of this project to me was when we finally got the model in the water. It was a long process to finally see the model go into the water and to see slow motion videos of just basic wave cases that they would have seen in Lake Michigan when they were using it, to see how dynamic that was. The bow was, dipping into the water.
By looking at the data that we acquired through testing, we're able to tell that the vessel did not go as fast as was historically recorded. This shouldn't be too shocking. The 1890s, early 1900s were the era of sensational news. So 20 knots was a bit of a stretch for this vessel. It was probably operating closer to 8 to 10 knots. Any kind of waves, they're quickly going to start coming over the deck, splashing up against the deck house, and getting all of the passengers wet, cold, and uncomfortable pretty quickly. As far as a vessel from 1890 that was all steel, required no ballast, and was powered by a locomotive engine, extremely successful. By modern day standards, it would be something that you would take out for a nice calm cruise around the lake. A project like this is very important for students' education because it allows them to take something such as an abstract thought, taking an idea and seeing it all the way through to the end to reality. So it's a full circle of what it really means to be an engineer.
We help them with how they approach problems and from an engineering standpoint, how they interact with their peers, how they can write reports, how they can present their findings, so with confidence, how they can weather changes.
It was exciting to work on the project as it was kind of my first hands-on experience being a naval architect. This is the first time really making a boat from nothing, doing the weights diagram, and then testing it in the tow tank.
Having the opportunity to explore this really old hull from the 1800s, that's kind of a once-in-a-lifetime experience. The work kind of felt like a detective case to me, where we didn't have solid data on this model, so being able to test it here at the MHL was pretty insightful to me and also very satisfying.
The AHA project has definitely kept not only Ephraim Shea's history, but Michigan maritime history alive. I do think that the AHA project really solidified my desire to go into naval architecture and marine engineering. Being able to actually experience it and on a hands-on team was very insightful to how naval architects and marine engineers work.
We always strive to have real-world application, to put our students into internships in the summer and have them be as connected as possible with industry. It's the perfect bridge between the fundamentals and the theory that we learn in the classroom and its application to answer new questions that were brought forth to us by the Historical Society.